A linear inequality is an inequality with two variables whose graph is a region of the coordinate plane bounded by a line. So we're going to graph a linear inequality today, and we're going to look at some linear inequalities. The line is the boundary of the graph. The boundary separates the coordinate plane into two half planes, one of which consists of solutions of the inequality. So a linear inequality is going to have a boundary line, and then we're going to shade the region of the coordinate plane where the solutions are. The solution to a linear inequality is an ordered pair. The solution to an inequality is an ordered pair that makes the sentence true, just like a solution to any equation or any inequality. And since this inequality has two variables, then the solution will be an ordered pair that makes the inequality true. Okay, so look at the examples here. When we graph a line on a coordinate plane, we split the coordinate plane into two regions. And the shaded region is the region where the solutions are. So to determine which half plane to shade, pick a test point that is not on the boundary. Check whether that point satisfies the inequality, and if it does, then you shade that region. That includes the test point. The origin is usually in each test point as long as it is not on the bound. In easy, that's supposed to be easy. That's a little typo there. The origin is usually an easy test point as long as it's not on the boundary, and I'll show you what I mean right now. So what is the graph of the inequality y is greater than 3x minus 1? So first thing we're going to do is we're going to graph the line y equals 3x minus 1. So I'm going to graph the line y equals 3x minus 1. The y-intercept is negative 1, and the slope is positive 3. So I'm going to go up 3 and over 1 and make another point. So the next thing I'm going to determine is if my boundary solid, which means I am including the boundary, or is it dotted, which means I am not including the boundary. So if I have a greater than, this tells me that I am not including the boundary. So what I need here is a dotted boundary. So I'm going to put a dotted boundary here. So then I'm going to choose a test point to decide where to shade. So I'm going to pick the origin. Now notice the origin is on the left side of this boundary line. So if I plug 0, 0 into this inequality, I get 0 is greater than negative 1. And that is a true sentence. So I'm going to shade the half plane where the test point is. So I'm going to shade this half plane, or the region where the test point is. If I would have gotten a false sentence, then I would shade the region where the test point was not. You can also inspect inequalities solved for y, such as y is greater than mx plus b, to determine which half plane describes the solution. Since y describes the vertical position, the solution y is greater than mx plus b will be above the boundary line. So let's highlight that. The solution y is greater than mx plus b will be above the boundary line, and the solution to y is less than mx plus b will be below the boundary line. So if you notice the example we just looked at, y is greater than, we shaded above the boundary line. But we're still going to pick a test point to make sure. So then we're going to look at this one. By inspection, graph the inequality negative 2x minus y is less than 2. So the first thing I'm going to do is I'm going to solve for y. So I'm going to add 2x to both sides. So I get negative y is less than 2x plus 2, and then I have to divide everything by negative 1. And so I need to remember that rule about dividing an inequality by a negative number. I'm going to change the sign to greater than instead of less than. Negative 2x minus 2. So now I'm going to graph my boundary line. So I'm going to graph 0, negative 2 as my y-intercept. The slope is negative 2. So I'm going to go down 2 and over 1. Make another point, and I'm going to draw a dotted boundary, so a dashed or a dotted boundary, since we are not including the endpoints, not including the boundary, excuse me. Okay, dotted. Hello, dotted. Okay, so we're going to draw a dotted boundary, okay, and then we're going to pick a test point. So I'm going to pick 0, 0. In this case, 0, 0 is above the boundary line. So I'm going to plug in 0 into the original inequality. Negative 2 times 0 minus 0 is less than 2. So that gives me 0 is less than 2, and that is true. So I'm going to shade where the test point was, above the boundary. You can graph two variable absolute value inequalities in the same way that you graph linear inequalities. So first thing I'm going to do is I'm going to get y by itself. So I'm going to subtract 1 from both sides. So I get negative y is less than absolute value of x plus 2 minus 1, and then divide everything by negative 1. So I get y is greater than, notice I'm changing the sign, y is greater than negative 1 times the absolute value of x plus 2 plus 1. So I'm going to graph the boundary, the absolute equation, y equals. So I see the vertex is at negative 2, comma 1. So I'm going to plot that. And then I see this one opens down. Notice I want a dashed or a dotted boundary. I want a dotted boundary this time. So I want to go down 1 and over 1, down 1 and over 1, make a point. And then I'm going to do a dashed boundary here. And since I see y is greater than means we want to shade above. So I'm going to shade above. In this case, I don't think it's necessary to do a test point because it is very obvious that the points greater than or above are v. So we can graph a linear inequality and make a boundary that's a line, or we can graph an absolute value inequality and make a boundary that is an absolute value function. You can use the transformations discussed in previous lessons to help draw the boundary graph more quickly. You can also use them to write an inequality based on a graph. So this one says, what inequality does this graph represent? So let's see. The first thing we have to do is come up with our boundary. And I want you to notice that this is a solid boundary. So it's shaded above. So since it's a solid boundary and it's shaded above, then we need greater than or equal to symbol here. So I want to do y is greater than or equal to, let's count our slope. Let's see. So I need to go up 1, 2, let's see, up 1, 2, up 1, 2, and over 2. So up 2 and over 2, that gives me a slope of 1. So I'm going to do y is greater than or equal to 1 times the absolute value of the vertex here. Let's see where the vertex is. The vertex is 1, 2, 3, negative 2. So 1 times the absolute value of x minus 3, and then minus 2. And I'm done. So exactly what we did yesterday. We need the vertex and we need the a, except we don't want an equal sign anymore. We want an inequality sign. And if it's a solid boundary, we want a or equal to. If it's shaded above, we want a greater than. If it's shaded below, then we want a less than. So we're going to do one more time, an absolute value inequality. So I see a dotted boundary, so that means just a greater than or a less than. And I do see it shaded above, which means I need a greater than. And my vertex is, let's see, that's negative 2, negative 4, up 2, up 3. So my vertex is negative 3, comma 3. Negative 4, comma 3. And let's count the slope. So I went down 1, down 2, down 3. Where's the next point? So we have to find another point on the graph. So I think it is, let's see here. We've got down 1 and, over 1. There we go. Down 1 and over 1, down 1 and over 1. So we have a slope of negative 1. So my a is negative 1. So I'm going to do y is greater than negative 1 times the absolute value of x plus 4 plus 3. And I did it.